In this problem, a solid circular shaft is to be designed to carry a torque of 750 Newton meters and a bending moment of 5,000 Newton meters. We are tasked to determine the diameter of the shaft without exceeding a shearing stress of 70 megapascals and flexural stress of 120 megapascals. And to solve this problem, we consider two cases to solve for the diameter of the circular shaft that is based on the shearing stress or based on flexural stress. And the formula for the shearing stress induced by a torque that is equal to dr over the polar moment of inertia. And for the flexural stress, that is the bending stress equal to m times c divided by the moment of inertia. So we're given a shearing stress of 70 megapascals or newton per millimeter squared equal to a torque of 750 newton meters. And to convert this into newton millimeters, we multiply this by 1000. And for r, which is the distance from the neutral axis or the centroid of the circle going to the outermost edge of the circle, that is a distance of the radius or half of the diameter divided by the polar amount of inertia for a solid circular shaft, that is pi d raised to the fourth power divided by 32. Now we can solve for the diameter based on the shearing stress using our calculator. We have 70 equal to 750 times 1000 times the diameter divided by 2 all over the polar moment of inertia. Shift solving, we get the diameter equal to 37.93 millimeters. This is based on shearing stress. Now, to solve for the diameter based on flexural stress, we are given a stress of 120 megapascals or newton per millimeter squared equal to the bending moment of 5,000 newton meters, or 5,000 times 1,000 newton millimeters, multiplied by the distance of the neutral axis going to the outermost fiber, that is just basically the radius of the circle, which is equal to d over 2, half of the diameter, and the moment of inertia for a solid circular shaft, that is pi d fourth over 64. Now we can solve for d based on flexural stress. We have 120 and 5,000 newton meter times 1000 times d over 2 divided by pi d fourth over 64. We get our diameter of the circle based on the flexural stress, that is equal to 75.15 millimeters. And based from these two values, the safest diameter would be the bigger one, to not exceed the shearing stress and flexural stress that is felt by the solid circular shaft. Therefore, our final answer is 75.15 millimeters.